Hello, welcome back to the session. Today, in the first half, Dr. Kalyan discussed about architecture of GPUs, right? He covered little architecture on A100, V100, and H100 cards. Okay. Today, I would like to discuss how to write a basic codes. Okay, by using NVIDIA GPU cards. Okay, for NVIDIA GPU cards. First, I would like to discuss a simple Hello World program. Uh, how can you write simple Hello World program by using simple GPU card? Here, how do you think? Actually, I discussed about MPI programs, right? When we look at MPI program, okay, GPU card is some device, one device. Your laptop or desktop is a host. Okay, here, suppose if you want to write a simple CUDA code, what we have to do is we have to establish a connection between this host and device. That means, yes, initially we are going to execute something. Actually, we want to execute something on the device, and we have to take those results, and we are going to display those results with the help of the CPU. Yeah, that is the context. How can we do that? Okay. First, I would like to discuss that particular one by considering very simple Hello World program. When you look at this Hello World program of a CPU, are you able to see the screen? Are you, I
Yes,
think
sir.
you are able to see the screen, right?
Yes, sir. Yes, sir.
Okay. Hello. This is simple Hello World program on C, in C, right? When you look at this simple C program, what can you see? You can see that there is a main function. This is a simple main function. This is simple main function. In this particular main function, we are going to call a function, another function that is a kernel, D kernel. Yes, in this particular D kernel, we are going to print hello, welcome on the screen. Hello, welcome on the screen. That is simple C program. Here, our objective is we want to write the same program. We want to print hello world, hello, welcome on the screen with the help of GPU device or with the help of GPU card. How can we do that? How can we do that? Okay. In the particular context, what we have to do is, first of all, from this particular main program, okay, we have to call the device, right? Okay. Who is responsible to call the device? Actually, um, compiler. Okay, compiler is responsible to call that particular device. Once we call that particular device, what we have to do is we have to execute something with the help of the device. After that, we have to get back the result. That is simple context. Okay, right. This is simple C program. We can use, we can compile this particular simple C program and GCC compiler. Similarly, suppose if you want to write the programs for the device GPU cards, we can write the programs for the GPU cards by using CUDA environment. CUDA stands for Compute Unified Device Architecture. Compute Device Unified Device Architecture. Okay. When you look at this particular one, at when you look at this particular simple code, here what can you see? What is the difference between that one and this one? Did you find any difference between the previous program and this program? Forget about this line. Anyhow, I commented this line. Okay. Forget about this particular one also. Like here, What is the difference between previous one and this one? What are the differences you observed as compared with the previous program?
D kernel function global.
Function name is same. If previously also we consider the same function, D kernel, right? Here also function name is D kernel. Okay. But when we look at the uh, prototype of this particular kernel, right, we added one term, right? Underscore underscore global underscore underscore. That means that that particular function is going to be executed on the kernel. That function is going to be executed on the device. Okay. Here, there is one technical term is there. Kernel means actually in CUDA programming or GPU programming, kernel means function that is going to be executed on the device or GPU card. Usually, we're going to call it as a kernel. Nothing great in that. Nothing great in that. Okay. For better understanding, I would like to code it right from the scratch. Okay. VI hello underscore CPU dot. This is simple C program. Okay. Suppose if you want to convert this one into the GPU code, what we have to do? We have to include one header file. What is that header file? Hash include CUDA.h. We have to include this header file. Now we included that particular header file. After that, we want to execute this particular one on the kernel. Okay, on the device. Okay, to execute this particular function on the device, we are going to declare this particular one. We are going to add a prefix to this particular function, that is underscore underscore global underscore underscore. Means that this particular function is going to be executed on the device. Later, what we have to do? We have to call this particular one from the main program. Main is here. Main is going to be executed on the host. That D kernel, that particular function is going to be executed on the device. We have to call that particular one. What is the syntax of this particular one? What is the syntax of this particular one? What is syntax of this particular one? Did you find the difference here? What is syntax of this particular one? We have to call D kernel. This is the function name. That function is going to be executed on the device. We have to pass some parameters. What are the parameters? One thread. So 1 comma 1. What is 1 comma 1? Do you have any idea? What is 1 comma 1? Do you have any idea? Please let me know. 1 comma 1 stands for
One thread, sir.
like C programs have extension with .c. Similarly, CUDA programs have extension .cu. Now we have to execute it. How can we execute it? To execute C programs, we are going to use GCC, right? Similarly, to execute CUDA programs, we have to use NVCC. NVCC, my hello.cu. We are going to store output file in my hello.o. It's successfully compiled. Now we are going to print or display the output. Yeah, nothing is displayed. Nothing is displayed. What may be the reason? What may be the reason? What may be the reason for that? The reason is that, okay, where is the main function is going to be executed? Where is the main function is going to be executed? Main function is going to be executed on the host. Usually CPU is called host. where the D kernel is going to be executed. D kernel is going to be executed on the device. Here, when we use this particular one, what are we going to do? We are going to call, we are going to execute this dkernel function on the device. Okay, right. After that, that device is responsible to print the statement on the screen. But before going to print that particular statement on the screen, this main function is going to be terminated because CPU cores are much powerful as compared with GPU cores. That is why we are unable to see the output. So to see the output in the multi-thread context, when we are working with multiple threads, there are two different threads are here, right? One is the CPU thread. This one is CPU thread. This one is the GPU thread. GPU thread is responsible to display that particular string, hello, welcome on the screen. But CPU thread, this is the master thread. This thread should wait for that four threads. Okay. Yes. Once all the four threads completed their task, then only master thread should be terminated. Is it clear? Is it clear? Or do you have any doubt? Suppose to get the output on the screen, what we have to do? We have to write a barrier in the main program. I discussed about the definition of the word barrier. What is the barrier? Barrier is the halting point. When we are working with multiple threads, okay, usually we write the barrier. Barrier is a halting point where fastest thread should wait for the slowest thread. Here, which thread is the fastest thread? CPU thread is the fastest thread. Okay. Here, GPU thread is the slowest thread. So here we are going to wait for the fastest thread should wait for the slowest thread. Okay. How can we write the barriers in CUDA? We are going to write the barriers in the CUDA program by using the function called CUDA device synchronize. By using function called CUDA device synchronize. Okay. Here, when we add the function, when we add that particular one, pi my hello.cu. If we add CUDA device synchronize, CUDA device synchronize. Okay. Now, actually, just now I added CUDA device. Now I'm going to execute it one more time. There are no errors. Now you can see the hello welcome on the screen. Hello welcome on the screen. Are you able to see the output? Are you able to see the output?
Yes, sir.
Yeah.
Yes, sir.
When we look at this particular simple program, uh, what are the takeaway points from this particular program? Okay. Suppose if you want to execute a particular function on the device, that means on the GPU, okay, either we have to use the prefix underscore underscore global or underscore underscore device. Okay. For time being, forget about underscore underscore device. Okay. Yes. Just consider underscore underscore global underscore underscore. That means that particular function or kernel is called from the host or main. Okay. After that, actually main thread should wait for that particular thread completes its task. Once that particular thread completes its task, then only main thread should be terminated. For that, we considered the function that is CUDA device synchronize. That is a barrier. That is a barrier. Next one. Here we are interested in how to print. Suppose instead of 1 comma 1, here now I'm going to execute this particular statement by using the syntax. Okay. And that is 1 comma 4 D kernel within triangular brackets. Okay. I put 1 comma 4. What is the meaning of that? one block and 4 threads per block. One block and 4 threads per block. That means that particular statement should be executed with the help of 4 threads, right? Are you with me? Are you with me?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
So now I'm going to execute that particular one, compile one more time. Now I compiled it. There are no errors. After that, I would like to execute this particular one. Hello, welcome. That particular statement is printed 4 times on the screen. Okay. In the next, actually here now I am interested in to print the thread number. If to print the thread number, usually thread number is integer value. So do you know how to print the integers? Integers can be printed with help of percentage d, comma. Okay, usually all these thread numbers will be stored in the variable thread
ID.
idx.x. Okay, that means thread numbers in the x direction. Okay, we can consider threads in x direction, y direction, and z direction. That is a kind of three-dimensional model. Later, I will discuss that particular three-dimensional model. Time being, don't particular three-dimensional model. Okay, with the help of this particular one, we can print a thread number. Okay, now I'm executing this simple program. When I execute this simple program, now you can see the thread numbers. Thread numbers 0, 1, 2, 3, 4. 0, 1, 2, 3. 4 threads. Now, okay, here, what I'm going to do is, instead of here, when we look at this particular dkernel function call, the first one is a dkernel, that is function name. That means function that is going to be executed on the device. Next, when within the angular brackets, what can you see? You can see the parameters. What are the parameters? There are two arguments. First argument and second argument. First argument is the number of blocks. Second argument is the number of threads per block. When we look at that particular one, here you can see one block and 4 threads per block. Okay. Now I'm going to change the parameter. Instead of one block, I considered 2 blocks and 4 threads per block. 2 blocks and 4 threads per block. In this context, when I execute this, what can you see? Here you can see that, okay, you can see a different output. 0, 1, 2, 3, again 0, 1, 2, 3. What may be the reason for that? What may be the reason for that? What may be the reason for that? What is the meaning of that? When you look at the parameter, what is the parameter there? Within the angular brackets, you can see 1, comma 4, right? 2, comma 4. That means that 2 blocks and 4 threads per block. Uh, these thread may belongs to one block. These 4 threads may belongs to another block. But we are not getting the unique thread ID. So to get, how can we get the unique thread ID? How can we get the unique thread ID? Any idea? Any guess? How can we get the unique thread ID? Yeah, meaning of that unique thread ID is actually when we are here, when we look at this particular parameters, what can you see here? We are going to launch 2 blocks, okay, and 4 threads per block. Okay, I'm interested to print thread numbers 0 to 7 because we are working with 8 threads. Those thread numbers are from 0 to 7. How can I print the thread numbers from 0 to 7? Any guess? Any guess?
One thread with 8 blocks.
Yeah. How can we get that particular one? A one thread with 8 blocks, that is simple and straightforward. Yeah. When you look at this particular program, this is also similar to the previous one. Here, what can you see? Here also, we are going to print hello world. Just forget about this particular statement. Here, parameters, I would like to call 2, 4. 2, 4. Okay. Here, I'm going to print the thread ID. Okay. Here, what is the difference between previous one and this one? What is the difference between previous one with this one? Here, I consider one statement. That statement is this one, right? With the help of this, we can get the unique thread ID. With the help of that particular statement, we can get the unique thread ID. What is that unique thread ID? How can I get it? Here, this one is block idx.x times block dimension.x plus thread idx.x. Okay. In this previous program, we discussed about thread IDs, right? Here, suppose I would like to give a simple idea on what is the meaning of this particular configuration. Meaning of that particular configuration is we are going to consider two blocks. We have two blocks, and this is
Each block 4 threads.
block 0. This is block 1, and 4 threads per block. This is thread 0. This is thread 1. This is thread 2. This is thread 3. That is 0, 1, 2, 3. Again, another block. We have 4 threads. Okay. We have 4 threads, sorry. 0, 1, 3. Right. Now, how can I, now with the help of this particular one, how can we get the unique thread ID? Okay. To get the unique thread ID, we can use the block number and this particular thread number. Okay, by using this particular formula, what can we see that? Here you can see that block idx.x. Here block ID is 0, this one, and block ID is 1 this for this particular one. This is the block ID. Okay. Next one. When we look at the block dimension in x direction, when we look at this particular one, block dimension in x direction, that means number of threads in x direction, that is 4 here. That is also 4 here. And this thread idx.x, this one, these are the thread IDs. Okay. When I use that particular formula here, what are we going to do? We are going to multiply these two. That is 0 times 4. After that, we are adding this particular thread ID. So with the help of this particular simple formula and this particular block, we'll get the thread numbers 0 to 3. And when we use the same formula here, okay, 1 times 4 plus that particular thread IDs, what do we get? Thread IDs from
0.
Thread IDs from 4 to 7.
We'll get 4 to 7.
4 to 7. In that way, we can generate the unique thread IDs. Are you with me? Is there any difficulty?
Yes, sir. Understood. Understood.
Yes, sir.
Okay, right. So usually, I would like to show a simple diagram to understand for better understanding. Are you able to see the screen? No, right?
No, sir.
Okay.
It's
Now,
coming.
can you see the
Yeah.
screen now?
Yes, sir.
Yeah. When we look at this particular one, what can you see here? Usually configuration is like this. Actually, here, what can you see? While launching a particular kernel, first argument is the grid dimension. Okay, that is grids. Actually, how many in grid consists of some number of blocks in x direction, some number of blocks in y direction, and some number of blocks in z direction. After that, okay, again, blocks also three-dimensional, right? That is number of actually when we look at the blocks, actually number of threads in x direction, number of threads in y direction, number of threads in z direction. Okay, with the help of this, we are going to launch um, some number of threads that are going to be executed on the GPU. Here, I would like to give a very simple example here. When you look at this particular slide, what can you see here? Here you can see that there are 4 blocks in x direction. Those numbers are block 0, uh, block 0, block 1, and 2, and so on, block 3. And 3 blocks in y direction, right? That is, you can see block 0, block 4, block 8, and so on, right? So when we look at this particular one, these are the grid dimensions. Okay, grid dimension gives number of blocks in x direction and number of blocks in y direction and number of blocks in z direction. If you don't give anything, then it is number of blocks in z direction is 1. Okay. After that, when we look at a particular block, here you can see that, okay, uh, block dimension dot x, that means number of blocks in x direction, this is x direction, that is 5. Number of blocks in y direction, this is number of blocks in y direction, and number of blocks in z direction, this is number of blocks in z direction. Okay. Based on that, here you can calculate from this particular, suppose if we launch the dkernel function with the following parameters, okay, then total how many threads are going to be executed? Any guess? Total how many threads are going to be executed? How many threads per block? Here, from this particular slide, you can guess how many threads per block? How many threads per block? How many threads per block? Any guess?
20, sir. 20.
How many threads per block? Here, when we look at the block, number of threads in x direction, number of threads in y direction, number of threads in z direction, right? We have to multiply these three things, right? 5 times 4, 4 times 3. So number of threads per block is 60. Are you with me?
60, yes.
Number of threads per block is 60. Next one is, okay, number of blocks per grid here. How many blocks are there in the particular grid? How many blocks are there in the particular grid?
12, sir. 12.
Well, so total number of threads is, with the help of this simple model, we can launch 12 times 60 number of threads. 12 times 60, it is close to, its value is 20 threads. That suppose if we consider this particular one, then we can execute that particular one with the help of 720 threads. 720 threads. Is it clear? Is there any problem? Okay. Now, actually, don't worry about this particular one. I would like to execute this particular one. You will get some more idea. Here, let us see. Consider. Here now, I am going to execute it with the help of mm, 4 threads. That means 4 blocks. This is 1D dimensional, right? And the number of threads per block is 32. Number of threads per block is 64. Okay. Mm, 128. Okay, this is very simple and straightforward model. What is the output of this particular one? Can you guess that? Here we are executing this particular D kernel with the help of 128 threads. What is the output? One block and 128 threads. If you execute that particular one with one block and 128 threads, what is going to be printed on the screen? What is going to be printed on the screen? Any guess? Any guess? Okay. Yeah, anyhow, I would like to use the same syntax. I think now you have comfortable with this particular myhello.cu, right? Forget about the previous one. Are you comfortable with this myhello.cu?
Yes, sir.
Yeah. Now I'm going to execute this particular one with one block and 128 threads. What is going to be executed? What is going to be printed on the screen?
128 times hello world.
128 times hello welcome is going to be printed on the screen. So when we look at that output, what can you see? Just to see this particular one, we are going to execute this particular one. Yeah. Now I'm redirecting this particular output to some other file, output 1.txt. Okay, now output is there in that particular one. When I open output.output1.txt, what can you see? You can see that numbers from 0 to 31. Okay. Okay, 0 to 127, you got it, right? Are you with me?
Yes, sir.
Are you with me? Now I'm going to execute one more time. Now see that particular output. Now here, what can you see here now? Numbers from 0 to, yes. Actually, my intention is I would like to show the execution based on the VOPs. Unfortunately, we got the output in at 0 to 127. Actually, in practice, that should not be the case. The reason behind that is VOP size is 32, right? Kalyan discussed about VOP, right? Are you with me?
Yes, sir.
Yeah. When we look at the VOP, uh, what is the meaning of the word VOP?
So a group of threads execute particular instructions.
Yeah, group of threads execute together, right?
Yes.
Okay. So that when we execute group of threads, actually what will happen is 32 threads executed together. When there's 32 threads executed together, actually we supposed to get first chunks of 32. Output hello welcome for chunk of 32. Okay.
Sir, in the previous class you showed also, sir. Actually,
Yeah.
the previous class you showed.
Okay. That's fine. Okay. In the previous class you showed, right? That is WAPs. Next one, net will be disconnected within a minute. Okay. Please join again. I think I am facing a problem with the Zoom. Okay. Right. Can I disconnect now?
Yes,
Yeah.
sir.
I
Yes.
will join again. Right.